Dear students, Assalamu alaikum. This section is a review of definitions and method of evaluation of the definite integrals. From our previous knowledge of elementary calculus, we associate the derivative with slope and the definite integral with area. But as the derivative f prime x of a real function y is equal to f of x has other uses besides finding slope of the tangent line, so too the value of definite integral need not be area, that is, under a curve. Recall if capital Fx is an antiderivative or primitive of a continuous function f, that is, capital F is a function for which capital F prime x is equal to fx, then the definite integral of f on the interval ab is the number f of b minus f of a. Remember that the fundamental theorem of calculus, just given in 1, is a method of evaluating integral a to b fx dx. It is not the definition of integral a to b fx dx. Now we move to the definition of definite integral. The definite integral of f on ab is integral a to b fx dx is equal to partition p implies to 0, limit partition p implies to 0, and a summation of k from 1 to 1 fxk delta xk. Dear students, you are already familiar with these notations. Here we just discuss how we will apply this definition to the line integrals. Whenever the limit in 2 exists, we say that f is integrable on the interval ab, or that the definite integral of f exists. The concept of definite integral, that is integration of the real function fx over an interval on the x-axis from xa to xb, can be generalized to integration of real multivariable function capital Gxy on a curve C from point A to point B in the Cartesian plane. Now we use some terminologies which will be helpful in the upcoming sections. Suppose a curve C in the plane is parameterized by a set of equations x as x of t, y as y of t, and t ranges from A to B, where xt and yt are continuous real functions. Let the initial and terminal points of C, that is x of a, y of a, and x of b, y of b, be denoted by capital A and capital B respectively. We say that C is smooth curve if derivative of x and derivative of y are continuous on the closed interval ab and not simultaneously 0 on the open interval ab. Figure number A shows that curve is smooth. 2. C is piecewise smooth curve if it is consist of finite number of smooth curves C1, C2 up to Cn joined end to end, that is the terminal point of one curve Ck coincide with the initial point of the next curve Ck plus 1. Figure number B, you can see that there are 3 smooth curves joined together. End point of C1 is joined with the initial point of C2. End point of C2 is joined with the initial point of C3. Number 3. C is a simple curve if the curve C does not cross itself except possibly at t is equal to A and t is equal to B. Figure number 4 shows an example of simple curve. Number 4. C is a closed curve if A is equal to B. Also, D is an example of closed curve. C is a simple closed curve if the curve C does not cross itself and A equal to B, that is C is simple and closed. You can see in figure number C that is closed but not simple because it crosses itself. The line integral of g with respect to x is integral a to b g of xy dx, and the line integral of g along c with respect to y is integral a to b g of xy dy, and the line integral of g along c with respect to arc length is a to b g of xy ds. Method of evaluation C defined parametrically. The line integral in the definition 5.1.2 can be evaluated in two ways, depending on whether the curve C is defined by a pair of parametric equations or by an explicit function. Either way, the basic idea is to convert a line integral to a definite integral in a single variable. If C is smooth curve parameterized by x as x of t, y as y of t, t from a to b, then replace x and y in the integral by functions x of t, y of t, and the appropriate differentials dx, dy, or ds by dx as x prime t dt, dy as dy prime t dt, or ds is equals to x prime t square plus y prime t square whole square root dt. Here the term ds is called the differential of arc length. In this manner, each of the line integral in the definition 5.1.2 becomes a definite integral in which the variable of integration is parameter t. That is, integral a to b g of xy dx is equals to a to b g of x t y t x prime t dt. Here you can see that we replace dx by x prime t dt. In number 7, we replace dy by y prime t dt, and in equation 8 we replace ds by x prime t square plus y prime t square square root. Now look at the example. When C defined parametrically, the question is evaluate integral C xy square dx, part B integral C xy square dy, and C integral C xy square ds, where the path of the integration C is the quarter circle defined by x equal to cos 4t, y is equal to defined by x equals to 4 cos t, y is equal to 4 sin t, and t from 0 to pi by 2. Here in figure number 4, path C of integration is described as it starts from the point 4, 0 and ends at the point 0, 4. And you can see that it's a quarter circle with radius equals to 4. Now we replace in the integral x by 4 cos t and y by 4 sin t. Now dx is equals to minus 4 sin t dt. So we have from 6 integral c xy square dx, and contours starts from 0 and ends at pi by 2. That these are the values of t. X is 4 cos t and y is 4 sin t, and dx is equals to minus 4 sin t dt, and after evaluation of the integral we will get minus 64. Similarly in part B, dy is equals to 4 cos t dt. So we have from number 7 integral c xy square dy is equals to t from 0 to pi by 2, x is 4 cos t, y is 4 sin t, and dy is 4 cos t dt, and after the integration we will get 16 pi. Note in this integration we have used two trigonometric identities. Sin 2 theta equals to 2 sin theta cos theta, and sin square theta is equals to 1 minus cos theta whole divided by 2. Since ds is equals to 16 sin square t plus cos square t, because ds is equal to x prime t whole square plus y prime t whole square root, and this will give you 4 dt. So it follows from equation number 8, we can write integral c x y square ds is equals to t from 0 to pi by 2, x as 4 cos t, y as 4 sin t, 4 dt, and it will give you the answer 256 over 3. Now we look at another method of evaluation c defined by a function. If the path of integration c is the graph of an explicit function y is equal to f(x), x ranges from a to b, then we can use x as parameter. In this situation, differential of y is dy equals to f prime x dx, and the differential of arc length ds is equals to 1 plus f prime t square whole square root dx. After substituting the three line integrals of definition 5.1.2, become in turn the definite integral as a to b g of x y dx will become a to b g of x f of x dx. A to b integral a to b g of x y dy will become integral a to b g of x f prime x dx, and integral a to b g of x y ds will become integral a to b g of x f of x, and ds will be 1 plus f prime t square root dx. A line integral along piecewise smooth curve C is defined as the sum of the integrals over the various smooth curves whose union comprises C. For example, to evaluate when C is composed of two smooth curves C1 and C2, we begin by writing integral C g of xy ds will be equal to integral C1 g of xy ds plus integral C2 g of xy ds. That is, integral C g of xy ds will be equal to sum of the two integrals C1 and C2. The integrals C1 and integral C2 are then evaluated in the manner given in equation number 8 or 11. Now for explanation, we look at these examples. In example number 2, C defined by an explicit function. That is, in this example, you can see y equals to x cube and x ranges from -1 to 2. So, replace in the integral y as x cube and integrate it from -1 to 2. We will get integral c xy dx plus x square dy equals to 132 over 5. And you can see in this example, when x is equals to -1, then y is equal to x cube will give y as -1, and when x is equal to 2, y equal to x cube will give 8. So the contour starts from -1 and ends at 2 8. Example 3, C is a closed curve. In this case, x is defined by cos t and y is defined by sin t, and t is from 0 to 2 pi. In this case, we replace x by cos t and dx by minus sin t dt. So integral c x dx is equals to 0 to 2 pi cos t minus sin t, and that will be equals to 0. In example number 4, C is closed curve. In this case, question is evaluate integral c y square dx minus x square dy, where C is the closed curve shown in the figure 5.6. You can see that this closed curve is comprises of the three curves. First is C1, then C2, and then C3. Since C is piecewise smooth, we proceed as illustrated in 12. Namely, the given integral is expressed as sum of the integrals. Symbolically, we write integral c as integral c1 plus integral c2 plus integral c3, where c1, c2, c3 are curves labeled in the figure 5.7. On c1 we use x as parameter. Since y is equal to 0, dy is equal to 0. You can see here that c1 starts from 0, 0 and ends at 2, 0, and here x is variable and y is 0. So we use x as a parameter and y as 0. On the curve c2, we use y as a parameter. From x2 and dx is 0, we have, because c2 starts from 2, 0 and ends at 2, 4, we see that x is fixed but y is a variable. So we take x is equal to 2. Therefore, dx will be 0. And integration of integrals c2 will give minus 16. On c3, we see that c3 starts from 2, 4 and ends at 0, 0. In this case, x varies down from 2 down to 0 and y also varies 4 down to 0. So here y is already defined as x square. So we get dy is equal to 2x dx, and so integral c3 y square dx minus x square dy is equals to x ranges from 2 to 0, x square whole square dx minus x square into 2x dx. It will give you the answer 8/5. Hence, integration of whole curve or the whole contour is equals to integral c1 plus integral c2 plus integral c3, and this will be equals to minus 72/5. Thank you very much.